Thank you for the introduction. It's fun to do this in finite time. So I'm going to be talking about some of my thesis work, actually, which is a weird thing to do at the end of your postdoc, but here we are. So we're going to start with my dark past, because see, these days I want to combine computer science and physics to measure things. We used to call this signal processing. On my postdoc, I mostly worked on kind of large-scale linear models, kernel methods, deep neural networks for inverse problems. But in graduate school, I was a Bayesian. I try not to admit this to my current advisor, but it's true. And I wasn't just kind of a loosey-goosey Bayesian. I was a hardcore Bayesian, publishing kind of novel models, novel sampling techniques. I actually had a Bayesian startup that got acquired. Like the whole, you can't drink the Kool-Aid, I think, much more than this. And part of the reason why I found kind of the Bayesian approach to statistics and machine learning so appealing is that actually kind of a lot of interesting data, I go so far as to say most interesting data is actually small data, right? When we think about kind of the anomalies that we're interested in understanding or kind of the social phenomena that we're interested in capturing, as scientists we're often interested in that weird thing out there, right? And often maybe you've distilled that down from some very large or big data set, but you often end up with a kind of much less data than you'd like. And this means that basically priors and uncertainty are going to matter, right? You're going to need to be able to incorporate prior knowledge or prior models, and you'd like to have some idea about how good or bad your result is. Now, fortunately, it's far easier to be a Bayesian than it ever has been, right? Probabilistic programming, which is an area I worked on a bit in graduate school in Josh Tenenbaum's lab, has really come into its own with tools like STAN, out of Andrew Gelman's group, Pyro from Noah Goodman's group, and PyMC. And these are all probabilistic programming languages that make it very easy for you to kind of write down rich, complicated probabilistic models and do kind of relatively automated inference in them. So why is this not what everyone's doing? Why are people fitting deep nets? Well, the kind of horrible secret here is that Bayesian inference is often very expensive. And by inference, of course, I mean in the statistical sense of fitting a model to data, not what the deep learning people call. So you can think of this as training Bayesian models is often very expensive. And this is exacerbated by the fact that there's kind of no more free lunch, right? So everyone who talks about scalable computing stuff likes to show these sorts of slides. For me, it's very personal because my life kind of mirrors this very interesting 52% per year growth period. So when I was listening to Nirvana and Weezer and Britney, computers were just magically getting faster. And then, we kind of hit these limits. Transistor densities are slowing. Not to malign the speaker after me, but it seems like Intel is having a lot of challenges shipping next generation process technology. So like things are not great. Like we're not going to get kind of as much free compute as we were hoping for in the past, right? So how can we make Bayesian computation faster, right? You can imagine kind of focusing on three parts of this process, right? The algorithms, kind of inference techniques, the software, including those probabilistic programming languages where maybe they do kind of automatic compilation and optimization and identify symmetries and conjugacy automatically for you. The part I'm going to talk about today is some work that we did on trying to figure out ways of making kind of hardware more amenable to kind of Bayesian inference. And my longer term vision for this was, and still very much is, trying to make some of this real time, right? I want kind of ubiquitous Bayesian instrumentation everywhere. And the key idea here is actually incredibly simple. What if we built hardware not to calculate, but to sample from distributions, right? So I'm going to give you an overview of this. So this is admittedly compressing a large fraction of my 20s down into the remaining 12 minutes. So it's definitionally going to be whirlwind. But I'm going to talk about the stochastic circuits approximation or idea that we came up with. I'm going to talk about ways of potentially automatically compiling these probabilistic programs, these probabilistic models, down to these sorts of hardware substrates. I'm going to talk about ways of kind of dealing with the fact that sometimes your model is too complicated. And then I might briefly, if I have time, touch on how do you deal with models with dynamic structure, where the number of variables is changing over the course of the execution. The underlying mathematical primitives or models here, we'll go through the basic probability. We'll talk about how you can use Bayes nets or directed graphical models and automatically compile them. We'll talk about Markov random fields, as physicists you may know them as Ising models, and ways of efficiently designing hardware to sample there. And then again, kind of, I think we'll probably end up skipping past the varying structure. But these all have kind of analogs with things that we think of as kind of AI today. So when I say stochastic digital circuits, what do I mean? Well, remember, Boolean digital logic, which underlies all of our common computing infrastructure today, is based on a couple of fundamental assumptions, right? One is this notion of kind of abstraction, right? The idea that you can kind of uniquely describe some box by the bits that come in and the bits that go out. But additionally, this notion of composition. I can glue these two things together very reliably, and then in fact completely abstract away their internals, right? And this is very natural when we think in the context of kind of Boolean logic. But of course, Boolean logic in this context is actually just probabilistic logic, but with delta functions, right? So what if instead we start talking about kind of gates or fundamental logic elements that produce samples conditioned on some input, right? So a classic example there, or I say classic just because I did it a long time ago, might be something you might call a theta gate, right? This is just a gate where you put in some probability, and then the output is a 1 or a 0 as if you had flipped a coin with that weight, right? So the nice example here is you can set some binary bits in. You can look at the time average of the outputs as you kind of digitally clock this thing. And unsurprisingly, you can weight whether you get more of a 0 or more of a 1, right? Now this has some really nice properties. The idea of gates that sample have nice properties, right? You can describe them with truth tables. And in fact, you can imagine describing kind of a classic AND gate here with probabilities that are just 1s or 0s, right? In kind of the digital limit or the deterministic limit. But you can talk about abstraction and composition. And in fact, the marginalization process is effectively kind of abstracting around that particular, those particular gates that you've concatenated together, right? So abstraction and composition is preserved. Now, let's look at composition in action. Well, with just this simple gate that can kind of flip a sample from a biased coin, we can come up with multiple ways of sampling from, say, a Bernoulli distribution. Maybe what we do is we have an accumulator that sums a bunch of coin flips. Or maybe we add those all together in general, or add those all together in parallel. We can kind of make this parallelism versus serial trade-off here. And this ends up being very powerful when you start trying to build systems like this. Now, all of these gates, because they're stochastic, require some source of entropy. Maybe that entropy is intrinsic. For everything we're talking about here, we're mostly going to focus on PRNGs, right? Pseudorandom number generators. Now, often people are like, don't this take up a lot of space? No, in fact, you can make very efficient tiny ones in silicon, so it's not really an issue. And of course, every device that you own has kind of tens, if not hundreds of these, because they underlie a lot of modern radio communication. But you might say, OK, well, Eric, we're building these low precision gates that sample. Isn't there a real precision concern here? But what's interesting when you think about trying to sample from two distributions, imagine you're just trying to determine whether or not these two coins are fair or slightly biased. It takes a very large number of samples. Right? This is kind of classic central limit theorem in action. It takes a large number of samples to see that there's a tiny difference. What that means is that in some sense, sampling provides a very natural substrate with which to work with low bit precision arithmetic, right? We're not talking, how do you express floating point numbers here? Instead, all the information is contained in kind of this time average of samples, right? We can even imagine building more complicated gates here that kind of take in arbitrary probability distributions, right? And very efficiently then sample from them, right? And what's really interesting is, the amount of silicon they use if you wanted to take, say, sample from a 16-sided die with arbitrary, or 16-sided die with arbitrary weights, right? Arbitrary probabilities of the faces, compared to a 64-bit FPU is considerably smaller, right? This can be a much more efficient way of constructing these systems. Say, well, Eric, that's fine, but I don't really want to sample from these sorts of simple distributions. Maybe there's something more complicated I'd like to produce samples from, right? Well, maybe we want to do something that looks like, say, Markov chain Monte Carlo, right? So every time, I actually thought it would be, Josh, if we do this again, we should have a bingo card. Because every time someone said, MCMC or ABC or any of these things, I was so excited. I was like, this is really much more fun than most machine learning conferences. So everyone understands MCMC, where you design a Markov chain that ergodically samples from some target distribution, right? Yay, it's a bivariate Gaussian. Well, of course, computers are very complicated finite state machines. And instead, you construct stochastic finite state machines, right? By connecting large numbers of these gates. And in fact, what you end up doing is kind of recovering MCMC in this limit, which is really exciting. But the neat part here, or a neat part, is that conditioned on the conditional independent structure of your probabilistic model kind of tells you how to parallelize this, right? If I sample a value for A, conditioned on that value for A, I can sample B and C independently. What this means is that the probabilistic structure of my model tells my other tools, tells me kind of how much parallelism can I get from a sampling perspective. So in my remaining 6 minutes, This is fine. You probably don't want to be a digital logic designer. I was for part of graduate school, and you'll note that I said I haven't touched this in a little bit. But we have the ability to compile these things, right? The rise of technologies like probabilistic programming let you kind of write down general purpose abstraction, compile those sorts of things through some compile graph here. This is from some arbitrary factor graph into the internals of, in this case, an FPGA, and get the resulting gate. So you can do kind of the standard BayesNet examples here. There's some Python code that we automatically compile into an FPGA. But you can do more interesting things like Ising models where you're capable of kind of dynamically varying the temperature, right? Hopefully this looks similar to some of you. We can then talk a little bit about kind of how do we deal with the fact that for a lot of problems, we don't actually have enough silicon to fully express the probabilistic model. And that's kind of this notion of vision. So one of the things we built along the way were kind of circuits for low-level perception that were enabled as kind of Markov random fields. So you can think of these as kind of non-homogeneous Ising models with external potentials or external fields. And what we're talking about here is basically having some external state, and we have these sampling circuits that kind of read in from some memory, do that stochastic stuff right out to that memory. I can talk about the parallelism, but the important part here is that it works, right, for things like, say, stereo vision, and it works at extremely low bit precision, right, where what you're capable of recovering is both kind of, in this case, an accurate stereo depth map, but at very low bit precision and very low power. We also showed it for optical flow. Fun fact, this is down on Addison when I was already out here doing the startup. But the part that we were surprised with is it actually worked for these kind of complicated probabilistic models, and again, with very little silicon. So I'm not going to talk about the continuous or the variable model structure stuff because there's not really time. So I think this abstraction is powerful. I think the fact that we can automatically compile or have the potential to automatically kind of translate these higher level languages into this low level representation is very useful. I think the fact that we don't have to make all of our circuits fully space parallel but can kind of intelligently and adaptively reuse resources is very enabling. And then, you know, there are many complicated models that I didn't really get a chance to talk to that we're still capable of capturing, right? And so why might this take off now? Why didn't I touch this for 5 years and then now I'm talking about this again? Well, for starters, I think these probabilistic programming languages here really get a lot of the credit, right? If you are still writing your own samplers, if you are still kind of writing down your own likelihoods, you might want to check them out. The amount of effort and engineering and kind of mathematical sophistication present in these packages is truly incredible. I guarantee you Stan's implementation of Hamiltonian Monte Carlo is better than what most of us could write. So the language part is here. But also, we're no longer terrified of custom hardware and of more ubiquitous hardware accelerators, right? In fact, the rise of technologies like TPUs, like Amazon's chip, and even, you know, Intel now owns an FPGA company, right? Who saw that coming? And so that means that kind of our hardware flexibility is much, much greater than it used to be. And also, for those of you thinking about, say, building very large telescopes or building very large particle detectors, the cost of ASIC design starts has really fallen, right? The cost to get a group of people together and build a new chip is actually considerably less at kind of state-of-the-art process nodes than it used to be. So that's one reason why I think people are less scared of hardware accelerators than they used to be. And it's not just us. I mean, this is a lovely paper from David Brooks' group at Harvard where, in fact, they're computer systems people, right? So like those of us who are in the RISE lab, they're very interested in kind of how do you build large-scale distributed systems? How do you make computers fast? How do you do these sorts of things? And they're starting to focus very closely now on these sorts of Bayesian workloads, right? Oops, did not want to. What did that do? There we go. So they have this new thing called Bayes Suite where they're just trying to develop ways of benchmarking these sorts of Bayesian problems, right? But, and this is the part I'm most excited about, more and more people are interested in novel computing substrates, right? Let's ask what happens when we go beyond Moore's law, right? If Moore's law is dead and we have to go beyond silicon. People are building interesting stochastic circuits elements now out of these various kind of spintronic or ferroelectric devices, right? So this is from 2017 and 2019, which may be a real testament of how long it takes your thesis work to kind of get anywhere. But I think this is very exciting because this starts to suggest that kind of maybe this isn't even going to work in the next 5 or 10 years, but it might be the right thing to do 30 years down the road. So in conclusion, probabilistic programming languages are awesome and I think are really going to change the way in which we model a lot of these problems. We can do this kind of automatic compilation to interesting hardware today. and maybe to exotic hardware tomorrow. And as was mentioned, I'm starting as a new professor this fall, so please come and be my graduate student or postdoc. That's it.
Thank you.